So what we looked at before was this idea, and you'll see this again, this is just written real tiny here, but 1/2 kx squared. That's what we came up with for the amount of work that a spring can do when it's squished. And basically, we talked about what work is. Work is the process of speeding something up. Energy is something that an object or some other thing has that gives it the ability to speed something up. So work is the process, energy is like the currency. That's how you get it done. And so what we were trying to figure out is, well, if I take a spring like this and I squish it a certain amount, how much work can it do, right? Work is the process of speeding something up. So any compressed spring could potentially speed something up. If it's pushing on something, it could make that thing go faster than it was before. So that means springs can do work. That means springs have energy. And what we were trying to figure out is how much. And what we arrived at looks weird. It's 1/2 kx squared. And we'll dive back into that in a little bit, but the k is the spring constant. Spring forces aren't always the same, but they have a linear relationship between the amount you squish the spring and the amount the spring pushes. So if you push a spring 1 centimeter, it'll push with a certain force. If you push with 2 centimeters, it will push with twice that force. The relationship between the amount you squish it and the amount it pushes is expressed in this spring constant K. It tells you how many newtons of force you get per meter or centimeter of squish. And then, so that part makes sense, right? You squish a spring and it pushes back with some force. And then we realized, well, as the spring expands, it'll push something, and the distance that it moves is equal to the distance that it's squished. And the force changes. The force starts out big and it ends at 0. So we realized, well, the average force is just half of whatever that maximum force was. Did a little algebra, and we came up with this. This doesn't look obvious, it doesn't look intuitive, but it's actually really simple. 1/2 kx squared. It tells you how much work the spring can do. So that work is the process of speeding something up. It doesn't tell us how fast something will go. It just tells us how much work it can do. And work is the process of speeding something up. So what is the connection between work and how much faster something can go? And that's what we're going to look at today. The kinetic energy has to do with moving objects, and the work kinetic energy theorem tells us how doing work to something changes its kinetic energy. Ultimately, the prediction we're going to make today is going to involve a supercart, and you're going to have a supercart that is launched from a spring. We can figure out how much work the spring can do with this, 1/2 kx squared. And with the work we're going to do today, you'll learn how to use that information to predict how fast that cart can go when it's launched. Okay? So what we're going to start with is just kinetic energy. Kinetic energy is not really that special. It's just energy. It's like chemical energy. It's like electrical energy. It's like any other kind of energy in that it's the ability to make something go faster. The thing about kinetic energy is we can see it. When you show me something and ask me how much chemical energy is in this piece of wood, I can't see that. If you ask me how much gravity energy there is in this ball in this position, I can't see it. I know there's energy there because if I drop it, it'll speed up. But it's really hard for me to know like how much there is. But with kinetic energy, we can see it. When something is moving, we know it has kinetic energy, all right? And then we're gonna look at this connection between work and kinetic energy that's gonna allow us to start making predictions. So kinetic energy is just the energy that a moving object has. What is energy? Energy is the ability to speed something up. We don't need a spring. I can take a cart right here and I can push it. And it's moving, it must have energy, and it can use that energy to speed up the other cart. It's that simple. Any moving object can make something else speed up. therefore it must have energy. If I throw a bowling ball at a bowling pin, the bowling pin will go from not moving to moving. It must have had energy. If I'm running behind, like, Jaden, because we're playing football together, I'm gonna tackle him. He's running away from me. I'm running toward him, I'm faster than he is, as you could probably guess. And I leap out and I tackle him, and as I tackle him, he speeds up a little bit, right? If I'm going faster than he is and I tackle him, I'm gonna push him in this direction. I had kinetic energy. I sped him up in the moments just before we go crashing to the ground. Jake on the bottom, injured, and we think, no, you're fine, because I don't weigh anything. So moving things can speed other things up. They have energy. And that kinetic energy is essentially telling us, well, if you speed something up, then you have to do work. The kinetic energy of a moving object tells us how much work that object can do, purely on the basis of its motion. And it's pretty easy to calculate. It's this. Kinetic energy is 1/2 mv squared. The mass of the object times its velocity squared divided by 2. We'll come back to most of this stuff in just a second, and all of it momentarily. But just real quick, let's look at the units here. The units of mass are going to be in kilograms. Velocity is meters per second. Meters per second, the quantity squared is meters squared per second squared. This is the same unit that we were using on Tuesday when we were talking about work. So kinetic energy and work both have the same unit, which is a joule. And that makes sense, because energy is the ability to do work. Work is the process of speeding something up. So if you have this much energy, you can do that much work. It's the same unit. It's not the same thing. Energy is a characteristic of an object. Work is the process of transferring energy, but the units are the same. Work tells us how much energy will be transferred. And you can see that, like momentum, this is a quantity that involves only mass and velocity. So if you increase an object's mass, it'll have more kinetic energy. If you increase its velocity, it'll have more kinetic energy. But unlike momentum, the velocity matters more. With momentum, it didn't, like they had the same weight, so to speak. If you doubled the mass, you doubled momentum. If you doubled velocity, you doubled momentum. But with energy, the velocity is more important. If you double an object's mass and keep its velocity the same, you will double its momentum. If you double an object's velocity and keep its mass the same, you will quadruple its kinetic energy. Work is the process of speeding something up. Momentum tells us how hard it is to slow something down. Those are two kind of different things. Momentum is telling you how hard something is to slow down. Work is telling us how much we can speed something up. They're two very similar but different things. Those of you who are into the calculus probably can see that kinetic energy is the integral of momentum with respect to distance. So what we're actually looking at here is a sum of kind of a thing. We're looking at the sum of momentum changes over distance. And you don't need to know that for this class, but it may help you in future classes if you're taking calculus. So let's come back to some of this other stuff. The first piece is, okay, the idea of including mass and velocity in kinetic energy makes sense. If we think of energy as the ability to speed something up, we think of kinetic energy as the energy something has because it's moving. It makes sense that things with more mass could speed things up more, right? Like if there's a big truck and it hits a balloon, the balloon is going to speed up a lot more than if it's just a tiny little like skateboard. And it also makes sense that faster speeds will give something more kinetic energy. Something is moving really quickly, it can speed something else more than if it was moving slowly. So that part makes sense. why is the velocity squared though? Like, why does velocity have like a exponential impact on how much something can speed something else up? That's not obvious. We can kind of think about it mathematically and just say, well, it matters more, that's obvious, but we don't know, it doesn't make sense why. Like, where did this come from? And then the weird piece is this 1/2. Where did that come from? Like, why, like, if I was gonna define kinetic energy in terms of mass and velocity, I would just say it's mv. But if you were like, well, that's momentum, I'd be like, fine, mv squared. Why put the half in there? If something's mass times its velocity squared is 10 joules, why do I look at that and say, okay, its kinetic energy is half of that? That doesn't make sense intuitively. But think about what we did with springs. We ended up with a 1/2 in there. The reason that we ended up with a 1/2 is because we had a force that was changing linearly. And we realized, oh hey, the average force is halfway between the maximum force and the minimum force. If the minimum force is 0, the average force is 1/2 the maximum force. That's where that 1/2 came from. This 1/2 comes from an average as well. And I'm going to show you where it came from. I'm going to walk you through this derivation. I don't expect you to know this or have it memorized, but what I would like you to see is that the work that we're doing here is ideally going to position you to understand this stuff on a more fundamental level than I can look up the equation, right? If I tell you an object has a mass of 4 kilograms and it's moving at 2 meters per second, what's its kinetic energy? Anybody can plug those two numbers into 1/2 mv squared. What I want you to be able to think about is, oh hey, there's a connection between work and kinetic energy that leads us to define kinetic energy as 1/2 mv squared. It didn't just come out of nowhere. So here's the framework for this is energy is the ability to do work. Work is the process of transferring energy. It's kind of a circular thing, which means we could ask two questions that essentially say the same thing. One is, if we have something with a certain amount of energy, how much work can it do? The other question we can ask is the opposite. If we do a certain amount of work, how much do we increase something's energy? It's the same question. So we can look at this from two different sides, the energy side and the work side, and it doesn't matter which one we put first in the equation. It's not really a cause and effect thing. So energy is the ability to do work. Work, as you can see down here, is force times distance. But the force that we're looking at is the average force. And I'm going to take a brief detour here to point out that in this case, this is the average of the force as the distance changes. It's a little bit different from the average force that we looked at in impulse, which is the average of a force over time. These two things relate to each other. We can put them together in a variety of ways. I'm going to blur the line between them for now. Just know it's not really the exact same thing, but as we get our amounts of distance and time smaller and smaller and smaller, they become the same thing. We're looking at limits here, and not everybody has the math to deal with that, so just like, trust me that this all works. And if you catch that there's a couple different ways to calculate average force, you're not wrong. There are a couple different ways. It turns out to be the same as we converge upon very small distances and very small amounts of time that go by. All right, so energy is the ability to do work. So something about the work that's done is reflective of the energy, right? If you do work to something, then you're going to change its energy. If you do work to something, you'll increase the amount of energy it has. You're transferring energy into something. So let's see if we can figure out how we can put all this stuff together to come up with something that involves, like, not just force and distance, but some sort of energy that we can look at. We know that we can think about kinetic energy. So let's make a couple assumptions. Let's make the assumption that the object that we're doing work to is only experiencing one force. That's not always true, but it's often true. If I push this supercart and I exert a force on it in this direction, there's hardly any force opposing my force. There's a little bit of friction, The track isn't perfectly level. Those are really small in magnitude. For the most part, the work that I do is going right into this cart. And in a collision, the work that cart does goes right into the other cart. And there's no other forces involved. So it's this sort of, this idea of sort of overall work is what we're looking at. That's not the same thing that we would see when there is friction. Like if I push on this cart, I could do some work to it, and it ultimately is like a little bit further away, but that's it. There's not any obvious energy that was transferred there. And that's because of all the friction involved. Friction was like doing work, but friction was doing work that kind of canceled out the work that I did. Or if you lift something up, if I do work on one of these bars, exert a force over a distance, at the end of my upward motion, it has no velocity. I haven't given it any kinetic energy. Why? Because I'm not working against gravity. And so gravity is doing work too, and gravity is doing work that cancels out the work that I'm doing. So if we assume that the work that we're talking about is overall work, there's no other forces involved, then what we can think about is what's called net work or overall work. And so let's jump to impulse for a second, because we have a connection here. Work has an average force in it, so did impulse. Impulse we define as the average force acting on an object times the amount of time that goes by. And what we said is, if there are no other forces acting on an object, then the impulse applied to an object will equal its change in momentum. So let's take a look at what we can do with that. If we start with this equation right here and rearrange this to solve for average force, we get that average force is equal to change in momentum divided by change in time. This has an average force in it too, so we can substitute. The amount of work done to an object is the average overall force applied to that object times the distance it moves in the direction of the force. That's going to be equal to the change in momentum of the object times the distance it moves divided by the amount of time that goes by. Right? This is just substitution. I just took this and substituted it in for average force. Change in momentum is final velocity times mass minus initial velocity times mass, right? This is change in momentum. That leaves me with displacement divided by the amount of time that goes by. So we just took a huge step, right? We've got some velocities in here now, but we aren't still quite to a place where we can use the amount of work that we do to an object to predict something about its change in velocity, because we still need to know this displacement and time thing, and that's just more stuff that we need to know. So maybe there's a way that we can avoid that, and there is. And that's this part right here. If we have a constant average force, which we will because we're taking the average force over a period of time, then we should have constant acceleration. And under the conditions of constant acceleration, we found that our definition of displacement, so here's distance an object moves divided by time, that is displacement divided by time, and that is our definition of average velocity. That is our definition of average velocity, displacement divided by time. As the amount of time gets smaller and smaller, the velocity, the average velocity converges on the instantaneous velocity of the object. But over any period of time, you tell me how far something has moved and in what direction and how long it took to get there, and I can tell you the average velocity. And I just want to break the fourth wall here real quick and point out there's some of you, I can tell, that you're not as locked in as you need to be. So let me remind you of what I'm looking for, which is I want you to be listening to and thinking about this. If you're not, I'm just I don't know what to do. What I really want to do is tell you to go do something that you are interested in. That would be my choice as a teacher, if I were an administrator, if I were the superintendent, I would tell all of you right now, go do the stuff that you're interested in, because I don't want you here if you don't want to be here. But if you're here, whether it's because you want to be or whether it's because you have to be, then I can tell you you'll get more out of it if you're focused. So this is worth thinking about. And if this is too hard for you, then I have 2 words of wisdom. Are you ready? You're wrong. You're not correct. This is not too hard for you. You can all do this. It's just that for some of you it isn't easy. It's not too hard. It's just that it's not easy. And if you're checked out right now because you're thinking, oh, blah, 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 math, then what I'll say to you then is just consider the fact that if all you've ever done is stuff that's easy for you, that's not really what, like, you haven't tested the limits of your capabilities. And those of you who are like, in athletics and stuff, you know what I'm talking about, because outside of the classroom, you know exactly what it feels like to challenge yourself and push your limits. It's not doing the things that you can't do. It doesn't mean that you try to run a 2-minute mile. It means that if your last mile was 3 minutes and 12 seconds, you're going to try to get your next mile to be 3 minutes and 10 seconds, or 3 minutes and 8 seconds. It's always a matter of finding where you are and doing slightly better. So just keep that stuff in mind, because I'm picking up on the 10 to 15% of you that just are not really engaged, and that's your thing. But I mean, there's value to the work that we do in here. Okay, so this gives us our average velocity, and way back when we were talking about kinematics, I said under conditions of constant acceleration, there is another equation for average velocity. And I said we didn't need it. We didn't really need it when we were doing kinematics, but we do now. And it's this right here. The average velocity of an object will equal its initial plus its final velocity divided by 2 when acceleration is constant. That's because if you have constant acceleration, acceleration is the slope on a velocity versus time graph. Your velocity versus time graph becomes a linear function. Just like force on a spring is a linear function of distance, velocity is a linear function of time, which means the average velocity is going to be halfway between the maximum and the minimal velocity. So we have an equation here for average velocity that's the same as d over delta t, which is right here. So we can substitute in, we can take this is our change in momentum, we can take this as our average velocity, and what we get is this, mvf minus mvi, that's our change in momentum, times, I'm going to take this part, vi plus vf times 1/2. Okay? This is the same as this mathematically. And all we've done are some substitutions. This is a binomial. This is going to be mvi vf. This is going to be mvf squared. This is going to be negative mvi squared. And this is going to be mvi vf, and it's negative. This term and this term are equal and opposite. We're still multiplying all this by 1/2, and what we end up with is 1/2 mvf squared minus 1/2 mvi squared. And that is the connection between work and kinetic energy. If all the work we do is going to increase an object's kinetic energy, then this is how much it'll change. That's where the 1/2 mv squared comes from. It comes from all of these mathematical connections. You don't need to know that, but I think you can. I think you can understand it. You might not be able to like do this on your own, but some of you could, but you don't need to do it on your own. What's cool is just recognizing, oh yeah, okay. It's not like somebody was just like, kinetic energy. You gotta have a kilogram, you gotta have a meter squared, you gotta have a second squared. I know, let's multiply mass by velocity squared and then divide by 2 just for fun. It came from definitions and laws. You can't get anything else but 1/2 mv squared for kinetic energy here. Work will speed up an object. How much will it speed up? Well, it's related to the square of the difference in velocities, or the difference in the squares of the velocities, the masses of the object. That's what work does. It increases kinetic energy. So that whole connection there, which you don't need to know the derivation, but you do need to know this final outcome, is called the work kinetic energy theorem. And basically what it boils down to is, if we do work on an object, and there's nothing else doing work to the object, then work will increase the speed of the moving objects. And the relationship between the amount of work done and the change in speed has to do with the change in kinetic energy. So our work kinetic energy theorem essentially looks like this. Overall work will change an object's kinetic energy by the amount of work done. What does that mean? That means if we know an object's kinetic energy at one time and we do work to it, we can add the amount of work that we've done to its kinetic energy to get its kinetic energy at a later time. Final kinetic energy minus initial kinetic energy will tell us the amount of work done to an object. And that means that all we need to know to figure out how much work will increase the speed of an object is the object's mass and its initial velocity. If we know its mass and we know its initial velocity, then we can solve for final velocity. And that's what you're going to be doing today. You're going to be using the amount of work done by our spring to calculate the change in kinetic energy of a cart, and then you're going to use that change in kinetic energy to make a prediction of how fast that cart is going to move after it's been launched. All right, so here's how it's going to work. The work kinetic energy theorem tells us that the work a spring does will increase the kinetic energy of whatever it's pushing, if there's no other forces, which is how we're going to set this up. So you've got to make sure that when you do this, your track is level and there's not a ton of friction. If there's other forces acting on your cart, then it's not, then the work that the spring is doing is not overall work. It's just work, but there may be other work that's canceling it out. If we start our cart at rest, which we're going to because you're going to push the spring all the way in and then lock it down, then the amount of work done is just going to be equal to 1/2 mvf squared, because the amount of change in kinetic energy is going to be 0 to whatever this is. And if we algebraically rearrange that, we get that the final velocity of an object is going to be the square root of twice the work done to it divided by the mass. That's just algebra. This is not anything that's obvious. I don't remember this. I would never remember this. What I can do is just derive it pretty quickly, and I don't expect you to be able to derive it from first principles, but you should be able to get from here to here, particularly if you're in AP physics. So how much work? Well, we looked at that, and I'm going to show you how to figure that out in just a second. I'm going to remind you of how to figure that out. But in this case, if it's a spring, if a spring is doing the work, then the amount of work that a spring can do is 1/2 times its spring constant times the amount of squish squared, which means we need to measure 3 things in order to be able to predict how fast a cart can go if it's pushed by a spring under the conditions of no other forces acting on the cart. We need to know the mass of the cart. We need to know how far the spring is squished before it's launched. Those are easy to measure. We get the mass, you already know the mass of the cart, it's 0.285 kilograms. If you put something on it, it'll change, but you can put it on a scale and figure it out. We can figure out how much the spring is squished. The easiest way to do that is to take a ruler, squish the spring, hold the ruler up, and you won't be able to get the 0 lined up with it, but you don't need to. I'm gonna line it up with 4. So I've got it lined up so that the top of that plunger is right at my 4 line on my ruler. And then when I release it and look at it, it goes to about 6.8. Right? I have to kind of line up perfectly. It's like maybe 6.9. So when you do the subtraction, it's about 2.9 centimeters, about 3 centimeters, right? Like you could just use 3 centimeters. There's like a millimeter or 2 isn't going to make any difference for what we're doing. So it's about 3 centimeters is how far we're going to squish the spring. But we also have to figure out K. So let me review that with you. We did this the other day, but I want to make sure that we're all on the same page, okay? So if you want to find the spring constant of a spring, the spring constant K tells us the amount of force per unit of distance the spring is squished. So to do that, take some measurements. Get your cart set up. You got to make sure that it's level. You got to make sure that the force sensor is zeroed. I recommend that you put one of these flat-ended rubber attachments on, because this seems to be giving us the most stable force measurements under these conditions. Once it's zeroed, then all you have to do is push in the plunger while the force sensor is pushing on something else. The force that the force sensor tells you is going to be equal to the pushing force of the spring because of Newton's third law, repeated a bunch of times for a bunch of things. And the distance is just how far you're pushing in the plunger. So that, you got to use a ruler again, and I'm not going to go get mine because you wouldn't be able to see it anyway, but you just put the ruler underneath it and you just kind of look. If I push this in a centimeter, measure the force. And then I'm going to push it in again, 1.5 centimeters, measure the force. Push it in again, 1/4 centimeter, measure the force. Whatever your distances are, you'll get a force. And you can graph those. The easiest way to do it, if you know how to use sheets, or you want to learn how to do this in sheets, I'll show you. The easiest way to do it is to take your data, put it into sheets, and make a scatter plot. You make a scatter plot, then your data should show up something like this. It's not going to be perfect, but it's going to be close. One of your data points, you don't have to measure, should be 0, because if you're not pushing on the plunger, there should be no force exerted by the spring or on the force sensor. You can draw a line of best fit, you can eyeball it, or you can use sheets to do it. I always use sheets. And then if you remember how to do this from algebra, you can calculate the slope of this line by just picking a point on this line here, picking a point here. The slope will be equal to the difference in y coordinates divided by the difference in x coordinates. If you use sheets, it'll do it for you. You just have it put a trend line in and have it use the equation as the label, and I can show you how to do that. K, our spring constant, is equal to the slope of this line. The change in y values is the change in force. The change in x values is the change in distance. Our average, our trend line here, our line of best fit, will have a slope that approximates the spring constant of the springs we're using. You have to do this pretty much every time you get a cart and start making measurements. You only need to do it once, but every time you get a cart, you need to do it. And the reason is because all the carts are different. So if you come in next Monday and you pick up a different cart, even if it's a yellow one, it's not the same spring. The springs are also adjustable. So even if you're like, I know, I'm going to look at this one, this ends at 7M6. I'm always going to use 7M6. I can change the spring constant of this cart by twisting the plunger. And it doesn't really change the spring constant of the spring, but it changes the extension of it. So now it's less. I just decreased it. And if I turn it the other way, then I can increase that spring constant. You can do this, it's okay to do it today, and you'll feel it. You'll feel the difference. Like, it's a lot harder to push. Even if you make sure that it's in the same place every time, you're not always going to get the same readings. And part of that is because today I'm going to suggest that if you pick up a cart and the plunger is all like squeaky, 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 take a little WD-40 and spray it in there, just the tiniest little bit, because that squeaky, squeaky, squeaky is friction that is reducing the efficiency of the work done by the spring. So if I put a little WD-40 on it, then WD-40 is not a great lubricant, but it does the trick for what we're doing. So now more of the work that this spring does is going to make the cart go, instead of just getting like all caught up in friction and stuff. And if you put WD-40 on there, you should just grab a little paper towel and make sure that there's not a bunch of like grease dribbling all over the place. And you'll probably find that your measurement's more accurate and your prediction is more accurate as well. So this is how you get K. And we know that the work done by the spring is going to be 1/2 kx, oops, kx squared. And we know that the final velocity of your cart, assuming it starts from rest, is going to be the square root of 2 times the work done divided by the mass of the cart. So that means if you measure the mass of the cart, the squish of the spring, and find that spring constant, you can make a reasonably accurate prediction for the final velocity of your cart when it's launched from a spring. And that's pretty powerful, right? Like that is, it's really different from like the kinematic stuff we were doing and the Newton's second law stuff that we were doing, because you can imagine like having energy in a variety of different forms. If we can figure out how to quantify the energy in something, as soon as we've done that, we can figure out how fast it could make something move. That's how, for example, we know how much fuel to put into a rocket. If we're going to launch a rocket, we need to know, like, well, how fast do we want that thing to be going up? And we got to put enough fuel in it so that it can get to that speed. In that case, the work is being done by the burning fuel. The energy that's being used is the chemical energy stored in the fuel. But this is how most of this kind of work is done, using the work kinetic energy theorem. Anytime you want something to go, it takes energy. How much energy? That much. That much to go that fast. It's really powerful. Okay. So if you need a break, take one. Otherwise, there's an assignment in Canvas. It's basically what I just showed you. Find out how much work the spring can store, predict how fast a supercar can go, test your work, and tell me everything you know about it. Okay?